Okay, so hello everyone out there listening. Welcome back to the Institute of Astronomy's YouTube channel. And as some of you might know already, because you've been following along with us, we are releasing these public interactive talks once a week, every week through this lockdown period. So while we're all socially isolating ourselves at home, we've got lots of nice astronomy for you to keep you entertained and to keep you educated while we're home educating. So this week is all about black holes, which is one of my favourite topics in astronomy. As you can see on our channel, we've had lots of different talks so far. We've had ones about the solar system, about looking for aliens, about stars, and last week about the birth of the universe itself. So if you like these talks and you want to hear more of them, give us a subscribe and you can learn about all the interesting things we're going to be talking about. So as always, we're doing this as an interactive session, and we're going to be using Slido. So Slido is a nice service where we can interact with each other through this talk. So there's two ways to access this. You go to slido.com, so you either take your mobile phone and type in slido.com, or you can scan that handy little QR code in the top left-hand corner there. And then so that's going to take you to the website, and then you use the code black hole to join in the conversation. I can see from George M and William and Samuel B, there's some questions being submitted already. That's fantastic. So the way the interaction is going to work, as this talk goes along, I'm going to be asking you guys some questions, testing some of your space knowledge. And at the end of the talk, there's going to be a question and answer session. So all of your lovely questions that are coming in as we go on through the talk, I'm going to answer as many as I can right at the end. So, like I said, this week is all about black holes, and I've called this talk Black Holes, the Weirdest Things in the Universe. And that is pretty much true. Black holes are incredibly strange, incredibly interesting. They're some of my favourite things in astronomy because they really test our knowledge to the absolute limit. So black holes are a bit strange. So I want to start with a much, much simpler question right before we go on to talk about black holes. I want you to think, how hard do you think you could throw a ball? Now, if you're anything like me, so let's imagine throwing a ball, right? I know it's a bit of a tease as we're all quarantined at home, imagining going and throwing balls in the park. So let's do a thought experiment, right? So say you take a ball and you go out into the park and you throw it up in the air as hard as you can. What's going to happen? So to start with, the ball's going to go up in the air, right? And then eventually gravity is going to pull it down to Earth. And how high the ball goes really depends on how good you are at throwing the ball, right? If you've got quite a rubbish throw, it might not go very hard in the air at all. If you've got a really, really good throw, you might be like a cricket player or a baseball player or something, then you might be able to throw it pretty high. But no matter how hard you throw, I want you to think about this question. Could you throw the ball into space? And the answer to that one is a pretty definite no, right? I mean, it doesn't really matter how hard you throw the ball. You'd never be able to throw the ball into space, right? So let's think about why. What is stopping you from throwing the ball into space? And the answer is the gravity of the Earth, right? So if you think about, if you're Superman, you could throw the ball into space, right? If you had a ridiculously strong throw, you could throw the ball into space. But if you as a normal person, you can't throw the ball into space. And the answer why is because of the gravity of the Earth. You can think about when you're throwing a ball, you can think about it being like basically a strength competition, right? Between your throw, which is, let's face it, pretty puny, compared to the gravity of an entire planet. And so what you're trying to do when you throw a ball in the air is beat the gravity of the entire planet. And there's just no way to do that, right? It's like your throw is just nowhere near strong enough. If you wanted to beat the gravity of the entire planet, you would have to throw the ball at about 40,000 kilometers per hour. That's how strong you would have to be to beat the clutches of the Earth's gravity and escape off into space. So that's never going to happen, right? No one's ever going to be able to throw the ball at 40,000 kilometers an hour. That's how fast you have to go to escape gravity. And so that's what we call the escape velocity, which basically means it's a scientific way of saying it's how fast you have to go to escape the clutches of something's gravity. So to beat Earth's gravity, you have to go that fast. So what about if we look at some smaller things where the gravity might be a bit weaker? So on the moon, gravity is weaker, right? That's why when we see astronauts jumping up and down on the moon like this, they seem to float around a bit, right? They take longer to come back to the surface. And that's because the gravity on the moon's surface is weaker. And so because the gravity is weaker, it's a bit easier to beat the moon's gravity and escape off into space. You'd only have to throw a ball at about 6,000 kilometers an hour to beat the moon's gravity. which is less than the Earth. It's easier to escape the moon than it is to escape the Earth. But it's still very, very hard. Throwing a ball, I don't know about you guys, I could not throw a ball at 6,000 kilometers an hour. So beating the moon's gravity is easy. If we have to find something that we can beat ourselves, we have to go to something very, very small. So this is Mars, but I don't want to look at Mars. I want to look at one of Mars's moons called Deimos. Deimos is a tiny little moon of Mars. It's basically like a big mountain, really, orbiting Mars. And the escape velocity on Deimos is just 20 kilometers per hour. So if you were on this tiny moon, you could easily throw a ball into space and beat Deimos's gravity. In fact, 20 kilometers per hour, that's, you could cycle at that speed, right? So you have to, if you're ever cycling on Deimos, be careful. If you go over a bump, you could easily escape off into space. So as things get smaller and smaller and the gravity gets weaker and weaker, it's easier to escape, right? What about if we go in the other direction? If we look at things that are bigger than Earth, where the gravity is stronger, it's going to be harder to escape. So Jupiter's a big planet, right? It weighs more than 300 times what Earth does. And so it's much, much harder to escape Jupiter's massive gravity. And in fact, you'd have to go at more than 200,000 kilometers per hour to escape Jupiter's gravitational clutches. So it's very, very hard to escape Jupiter. And so you can see the general pattern, right? You can look at different things, and depending on how strong the gravity is, from weak gravity up to strong gravity, it depends on how easy they are to escape. So small things that have weak gravity are pretty easy to escape. You don't have to go very fast. And the stronger the gravity, the faster you have to go to escape them. So things like Deimos and the moon, pretty easy to escape. The Earth and the big things like Jupiter with strong gravity are hard to escape. So we've kind of got a list here of things that are harder and harder to escape, where you have to go faster and faster because the gravity is getting stronger and stronger. So what do we think the end of the line is? Let's try and go to the very end of the line here and say what's the hardest thing to escape in the universe. And another way of saying that is what is the fastest thing in the universe, right? So we have to go pretty slow to escape the moon, a bit faster to escape the Earth, a bit faster to escape Jupiter. What's the fastest speed there is? Because then we can start thinking about what's the strongest gravity there is. So I'm going to go to a question for you guys. What is the fastest thing in the universe? I've got a list of some things out there that are all pretty fast. And I want you guys to have a think and tell me what you think the fastest thing in the universe is. Because once we've decided what the fastest thing in the universe is, we could then have a think about what the strongest gravity in the universe is, which is going to get onto the topic that we are talking about today. So I'm going to give you a moment to think about it. So Voyager 2 is a spacecraft that was launched about coming up to 50 years ago now to explore the outer solar system. It's one of the fastest things that humanity has ever produced. The Andromeda Galaxy, a big galaxy coming towards us at hundreds of kilometers per second. We've got neutron stars, we've got light, and we've got cosmic rays, which are these really high energy particles that can crash into Earth sometimes. Let's see what you guys are saying. I'm starting you off with quite an easy answer. I'm guessing quite a lot of you would have got this. The answer is, as nearly 90% of you have guessed, the answer is light. Light is the fastest thing in the universe. So well done to all of you that got that right. So the fastest thing in the universe is the speed of light. Oh, and that is my quiz question. The speed of light is over 1 billion kilometers an hour. It's so fast that it makes everything else on that list look so slow it may as well be standing still. The speed of light is an unbelievably fast thing. So the very, very top of this ladder is the speed of light, right? So low escape speed up to high escape speed. The very top of this ladder is the speed of light. So is there anything here where the gravity is so strong that you need to go the speed of light to escape? And what about gravity even stronger than that? Is there anything up here that is so strong that even the speed of light won't let you escape? What if you're trapped even at the speed of light? Because if the escape velocity of something is faster than the speed of light, if the gravity is so strong that even light can't escape, that object is going to be invisible, right? You're never going to be able to see it. The first person to realise this, it's actually really interesting, was a long time ago. There was a guy called John Mitchell who was a scientist nearly 250 years ago, and he's the first person to realise this. He called these things dark stars. The idea was that if a star was so big and had such strong gravity, not even light could escape, we wouldn't see them, because all the starlight that the star was shining out into space would just get kind of sucked back in by the star's gravity. And so, if you imagine holding a torch on the surface of one of these objects and shining your torch up in the air, the beam of light, just like throwing the ball in the park, the beam of light would go up and up and up and eventually would get pulled back down by gravity. And so, if you were trying to send a signal to your friend on a spaceship, for example, near the object, you wouldn't be able to signal them because the signal from your phone or the signal from your torch would get sucked back down to by the gravity of the object. So any object where the gravity is strong enough that the escape velocity is faster than light is actually invisible. Or in other words, it would be black. And so, of course, what we are talking about here are black holes. So black holes are any object where the escape velocity is faster than the speed of light. So it's any object in the universe that has such strong gravity that nothing, not even light, can escape. And this is what we think a black hole looks like. So this is a computer simulation of what it would look like to be near a black hole. And so you can see the black area is obviously the black hole. But there's also something interesting. So the first thing you notice is that it's not just a black hole, right? Why doesn't the black hole just look like this? It's not just a black cutout in space. It's a black cutout in space, but that's surrounded by this cool kind of hall of mirrors, kaleidoscope type effect of all the light bending round it. And that's there because of the strong gravity of the black hole. If all the light that's around the black hole coming from distant things is bent around by the gravity of the black hole, because the gravity is so strong. And so that's why you don't just get this round circle, you get this kind of amazing hall of mirrors kaleidoscope effect as well, as black holes kind of bend and shimmer the light all around them. Although black holes are very dangerous, I think they would be very beautiful objects to see. So let's take a closer look at our black hole. So this is, it's a simulated black hole. It's a computer drawing of what we think a black hole looks like. The first thing you notice is called the event horizon. The event horizon is this edge of this black circle. And what the event horizon is, it's the point of no return for the black hole. So I was saying before that black holes are things that you can never escape, even if you travel faster than the speed of light. And because nothing can go faster than light, nothing can escape. The event horizon is the point of no return. So if you were in a spaceship orbiting around a black hole or flying around a black hole, as long as you had good engines, you could fly around as much as you wanted and be safe. But as soon as you cross the event horizon, at that point, you're trapped inside the black hole. The interesting thing is that you might not even notice that you've crossed the event horizon. There's going to be no barrier or sign, and so especially for a big black hole, you could just be drifting happily through space and not even know that you've crossed the event horizon near it. Because it's a bit like the point of no return for a waterfall or something, where no matter how hard you swim, you're definitely going to go over the waterfall. If there's no sign there, you might not even know it. But it is possible to drift over the event horizon, and at that point, you're completely trapped. There's nothing in the universe that can save you, because the only way to escape would be to go faster than the speed of light. And because nothing can go faster than light, because that makes Einstein very unhappy, then you can't escape. So that's why it looks like this black circle on the sky, because all of the light that is inside the event horizon gets swallowed up and can't escape. So the event horizon marks the edge of our black circle in space. But what about inside? So if this is the event horizon, the kind of circle around the edge, what's in the middle of the black hole? So let's take a closer look and zoom inside the event horizon and take a look. So right inside the black hole, in the very middle, there is a tiny dot. And this tiny dot is called a singularity. And you can think of the singularity as like the heart of the black hole. It's the tiny, tiny dot inside where all of this huge, ridiculously strong gravity is actually coming from. So the singularity is the tiny dot that's the heart of the black hole. The reason it's called a singularity is because it's actually infinitely small, which, I don't know if you're anything like me, that's almost impossible to get my head around, something that's infinitely small, smaller than a grain of sand, smaller than an atom even, just an infinitely small dot in space. But even though it's an infinitely small dot, it does weigh a lot. So a black hole might weigh as much as a star. It's an entire star's worth of stuff squashed up into this infinitely small speck in space. And singularities are almost beyond our current understanding. They stretch our known laws of physics to the absolute limit and beyond. So we still have a lot to learn about what singularities actually are. One of the reasons we have a lot to learn about them is because the event horizon stops us knowing about them, right? The event horizon is a really effective barrier that separates the singularity from all of the people outside. Because nothing can escape the event horizon, that includes signals, that includes information about the singularity, right? And so anything that's going on inside the event horizon is a complete mystery to everyone outside. So that makes it really, really hard to learn what's going inside if there's absolutely no way any signals or information could ever come out. So this is one of the reasons that black holes are incredibly mysterious things. So how do you form a black hole? We're talking about, so this is what black holes are, right? They have an event horizon, they have a singularity in the middle. How do you form something so ridiculously extreme? So to form a singularities are very small, right? So to form a singularity, you obviously have to take a bunch of stuff and squash it up really, really small. So let's talk for a minute about squashing things up really small. In general, you squash things up by squeezing out all of the empty space, right? So think about a sponge. Sponges are nice things to think about because they squash up very, very easily. So think of a sponge that you used to do the washing up or you have in the shower. You can squash a sponge in your hand really easily, right? And that's because a sponge is full of empty space. There's lots of air holes inside a sponge. And when you squish a sponge down, all you're doing is you're squashing out the air, right? So the general rule is you can make something smaller by squashing out the empty space. It's the same way you might, after you finish drinking a can of Coke, you might crush the can down, right, and small in your hand. And what you're doing there is squashing out the empty space. Or if you take a car to a car crusher, if you imagine one of those big machines that crush cars, you can recycle them, they squash out all that empty space inside the car. And the more empty space there is, the smaller you can squash something. It's the same reason you could take a really big marquee or a really big tent and fold it up into a really tiny bag. It's because inside a tent there's absolutely loads of empty space. So the more empty space you've got, the smaller you can squash something down. So let's think about how small it's possible to squash something down. And I want to ask you the second question here. So this is a slightly trickier question. I want you to think about how much empty space there is in stuff, particularly your body, right? So how much of, I would say, I mean, for your body, think of all of matter, right? But it's kind of fun to think about ourselves. How much of us is empty space? Because this is going to dictate how small we can get squashed down. Okay, so have a think about this. The options are a quarter, a half, 3/4, 90%, 99%, or even more than 99%. So I'm going to give you a few moments to have a think about what the answer might be. And while this is happening, I'm going to have a look through some of the wonderful questions that you've been submitting. Okay, answers are coming in. Let's have a look at what you guys are saying. Interesting. So the top answer is 25%. The second top answer, the very other end of the scale, more than 99%. So very, very split here. About a quarter of you thinking that 25% of your body is empty space, and then about another quarter would say it's more than 99%. Okay, I'm going to go to the answer now. This is an absolutely mind-blowing space fact. So anyone that said the answer is more than 99% is correct. That is the right answer. More than 99% of you is empty space. And it's actually a lot more than 99%. It's 99.9999999% empty space, which is kind of amazing, right? Almost all of you is empty space. And that's true of all of the stuff around us as well, like you and the floor or the sofa or the chair that you're sitting on, and your dog or your cat or your house, and the earth itself is almost entirely made of empty space. How can that be possible? So the answer is that we're all made of atoms, right? Atoms are like the little Lego bricks that make up everything in the universe. If you had the most powerful microscope ever, you could zoom into your hand or your chair or the wall next to you, and you would see it was made up of these little atoms. They're the Lego bricks of the universe. And atoms are mostly empty space. So atoms have, you might have learned this in school, the atoms have a nucleus in the middle, they have some electrons in them, but most of the atom is just a big empty space. So atoms are 99.9999999% empty. And because atoms are that empty, that means everything that's made of atoms is that empty. And because everything in the universe, or all the matter, all the stuff in the universe is made of atoms, that's how empty everything is. So remember we said that the smaller something is, also the more empty space there is in something, the smaller you could squash it. With this much empty space and stuff, you could squash it up really small indeed. This is just an example. This is one of the most mind-blowing facts to me. If you removed all of the empty space in the atoms, the entire human race would fit into a single sugar cube. And I don't know if you're like me, but that completely blows my mind. That shows you how much empty space there is in everything. So you could fit the entire human race into a single sugar cube just by getting rid of all the empty space. So it's possible to squish things up really, really small, right? What's the absolute smallest you could squeeze something down? Because the answer is, if you squeeze something down enough, the smallest you could squeeze something is into a black hole. You have to squeeze out all the empty space and then basically keep squashing so all the atoms start overlapping, which they don't like doing, so you have to squeeze very, very hard. You in fact have to squeeze the moon down until it was about as big as a grain of sand. So if you could take the moon and squash it into a grain of sand, it would be a black hole. And so the interesting thing is that absolutely anything in the universe can become a black hole if you squash it small enough. It doesn't really matter what a black hole is made of. You take any stuff and squash it enough and it would become a black hole. You take the moon and squash it down until it was the size of a grain of sand, it would become a black hole. So that's how you make a black hole. You basically take anything and squash it up really, really small. So what could be powerful enough to do this? I mean, it's very easy to say, let's take the moon and squash it down into a grain of sand, but what in the whole universe could possibly have enough energy and have enough power to do something like that? The answer is a supernova. So supernova is an exploding star. We spoke about these a couple of weeks ago in our Life of Stars YouTube talk. Supernovae are some of the most powerful things in the entire universe. A single star going supernova can outshine an entire galaxy. This is a picture of a star going supernova and a galaxy that the star is in. And the star going supernova is brighter than the whole galaxy added together, even though the entire galaxy contains hundreds of thousands of millions of stars. Supernovae are some of the most powerful and extreme things out there in the entire universe. And they're the kind of things that have enough power, that have enough energy to squash things into a black hole. So black holes are formed from the very biggest stars of all when they go supernova. This is an artist drawing of one of these really, really giant stars that is right at the end of its life and about to explode into a supernova. The way it works is, so this is my cartoon drawing of a star. The outer layers of the star are the things that explode and kind of go off. And so when you see a supernova here, this kind of like nice explosion-y stuff you're seeing is all the outer layers of the star that are kind of blowing off in that giant explosion. So the outer bits of the star explode as a supernova, but the inner bits of the star get crushed down by gravity. And so the core of the star actually shrinks and gets smaller and smaller and smaller until it becomes a singularity, which is, if you remember, what we said a black hole was. So this is how you create a black hole. You take a star, and it has to be some of the biggest stars of all, more than 10 times bigger than our sun. And when they explode in a supernova at the end of their life, the outer bits blow off, and we see that as a big giant explosion. But the inner bits, the core of the star, gets squashed down smaller and smaller and smaller by gravity. And there's enough stuff, and the gravity is strong enough that it has that power to squash it small enough to become a black hole. So that's how lots of black holes are formed. They're formed when the biggest stars explode. Interestingly, there's actually two types of black hole. I've been saying black hole like they're just one type of thing. There's actually two types of black hole. There are what we call stellar black holes, and there are supermassive black holes. So stellar black holes, the word stellar means to do with stars, right? And so as it might sound, stellar black holes weigh roughly about the same as a star, and they're the ones that are formed when really big stars die, like I was just saying. And these black holes are pretty common. There are millions of these per galaxy. On the other hand, there are supermassive black holes, and the clue's in the name, right? They can weigh millions of times as much as a star. There's only one supermassive black hole per galaxy, and they live right in the middle of the galaxy, and they're formed at the same time as the galaxy. So these ones are not formed when big stars explode. They're born at the same time as a galaxy. So stellar black holes, millions of them, very, very common. The supermassive black holes, they can weigh as much as millions of stars, and they're very special because there's only one per galaxy. So every galaxy will have a supermassive black hole in the center. Our Milky Way, for example, has a supermassive black hole in the center. This is an artist drawing of our Milky Way, and there's a supermassive black hole right in the middle. We know there's a supermassive black hole in the middle of our galaxy because we can take our telescopes and look at the stars orbiting around in the center of our galaxy, and we can just see them orbiting nothingness. So this is a nice video that was put together by some astronomers at the European Southern Observatory, and it's sort of showing the stars orbiting in the very, very heart of our galaxy. And just like in our solar system, where the planets orbit around the sun because of the sun's gravity, we can see stars here orbiting around the completely invisible. So it has to be a black hole. So there's a black hole at the center of our galaxy, and there's a black hole in the center of every galaxy. I want to show you this picture. This is a very, very special picture. So the photo of the black hole I showed you before at the start of the talk was not a real photograph, right? That was a computer simulation of what it might be like to be in a spaceship near a black hole. This is a real photo now of a supermassive black hole in a galaxy called M87, which is about 50 million light years away. And this is a brand new photo. It was only taken very, very recently. So everyone alive today looking at this picture, we are some of the first people in history to ever really know what a black hole looks like. Taking a photo of something like this 50 million light years away was unbelievably difficult. They used something called the Event Horizon Telescope, which is a network of telescopes all over the sky. And being 50 million light years away, from our point of view, it's really, really tiny. Taking this photo was the equivalent, in terms of magnification, of reading the lettering on a coin in New York using a telescope in London, which completely blows my mind, right? It's such a tiny, tiny thing out there on the sky to take a photo of. But we did it, and we are able to get a real photo of this black hole. So to explain what you're looking at, it looks a bit like a fuzzy orange donut, doesn't it? And so the inner ring of the donut, the whole of the donut, is the event horizon. And that's why it looks like this kind of black hole area. It's black because it's swallowing all the light. So we're actually looking at the event horizon of this supermassive black hole. The inner core is where all the light is being kind of sucked up, and nothing is escaping. But the fuzzy bit around the edge, the fuzzy orange donut. So what's that? If black holes are black, why is this one kind of glowing so brightly? The answer is that all the stuff that the black hole is gobbling up, right? All of the stars and the gas and the planets that are being swallowed up by this black hole are swirling around it like water swirling around a plug hole. You can do an experiment, right? If you swirl water around a plug hole and drop in some food colouring, you can see that it kind of swirls around in this nice pretty pattern before it gets sucked down the plug hole. And that's pretty much what's happening to all of this stuff around the black hole. So this orange glow is all the stuff that's swirling around the black hole being gobbled up. So this is a supermassive black hole. So this is one that weighs much, much, much more than a stellar mass black hole. And in fact, this black hole weighs somewhere around 5 billion times as much as the sun. That's 5,000 million suns. I'm going to show you a nice video that a YouTube user put together of what 5 billion suns really looks like. Because again, if you're anything like me, 5 billion suns is almost too much to imagine. So we're going to take this one sun, and we're just going to keep on adding suns until we get to a number, until we get to about 5 billion. So you can see how big that number actually is. So we start with 1, and then we're just going to add suns over and over again. So we can get a big square of about 10,000 suns, and then we turn that into a cube of about 1,000,000 suns, and then, but even that's like nowhere near, right? So we have to just keep adding and keep adding and keep adding. This video always completely blows my mind. So this is now 5 billion times the mass of our sun. So if one of those little things was our sun, this is how much mass is in that very, very giant black hole that we took a picture of. Okay, time for everyone's favourite topic. We're near the end now. What happens when you fall into a black hole? So let's go back to our spaceship that was happily orbiting around the black hole before. What's going to happen to the spaceship as it gets towards the black hole? So first of all, the spaceship is going to cross the event horizons. And like I said before, it might not be very obvious to the spaceship when it's crossing the event horizon. There's no bump you go over, there's no sign in space. You're probably happily drifting through space near a black hole. So you would know that you were near a black hole, right? It's not going to happen to an astronaut or something. But if you're near a black hole, it's at some point you would cross the event horizon. And at that point, the spaceship is lost to the universe. It can no longer communicate with the rest of the universe. So from the outside, the spaceship would have seemed to have vanished. But let's kind of stay with it. Let's stay with this doomed spaceship and see what's going to happen. So it's going to get closer and closer and closer to the singularity. Because remember, the singularity is the heart of the black hole. It's the thing that's powering the black hole. And the incredibly strong gravity from the singularity is going to pull the ship in closer and closer and closer. After a certain point, when the ship gets very close to the singularity, something very strange happens. So if you think about the ship here, so we've got our ship above our singularity, the very bottom of the ship, that's closest to the actual black hole, is going to feel some very, very strong gravity because it's closest, so it's going to get pulled really hard. And the very top of the ship, which is furthest away from the black hole, is going to feel gravity a bit less strongly, so it's going to be pulled slightly less hard. And so because the bottom of the ship is pulled the hardest, the whole ship is actually going to be pulled out really, really long and thin by the gravity of this black hole. And then just after this ship is pulled out really long and thin, in about 1/1000th of a second, then it will be swallowed by the singularity and squashed to nothing. There's a real scientific word for this, which is, I think, my favourite scientific word of all time. So when things are pulled out really long and thin by the gravity of black holes, it's called spaghettification, which I sometimes can't believe is a real scientific word, but it is. So spaghettifying is when you get pulled out really long and thin by the gravity of a black hole. Luckily for our doomed astronauts, this would happen in about 1/1000th of a second, so they probably wouldn't even know it was happening. So almost time to do some questions. Right before we do, I want to just kind of bust 2 black hole myths, because I think people often have some misconceptions about black holes. I want to say that 2 things that black holes are not before we go on and answer some questions. So first of all, black holes probably aren't wormholes. So this is the idea of a wormhole as like a tunnel through space that you could travel to and explore different parts of the universe. And it's a really popular idea in science fiction, right? The idea that you could travel through these tunnels in space, and if we were some super hyper advanced civilization, we might be able to build these wormholes and explore different parts of the universe. Unfortunately, this probably doesn't work. It's almost certain that wormholes that don't really exist. So they are theoretically possible. It's possible to write down some equations, the equations of relativity, and make a wormhole in the equations. But first of all, we've never actually observed a wormhole in the real universe. And secondly, we're not really clear how one would actually get made. So black holes probably aren't wormholes. I have to use the word probably because black holes are very mysterious and we don't know what's happening beyond the event horizon. But as far as we can tell, black holes are not ways to travel through the universe. It's probably a good way to get yourself squashed to bits. The second thing, and the last thing I want to say, is that black holes aren't just cosmic vacuum cleaners. I think a lot of people think of black holes as kind of big cosmic hoovers that go around sucking up all kinds of material in the universe. And while that is true, you have to get very close to a black hole to be kind of sucked up by its gravity. If you are far away from a black hole, it just acts like an object with gravity like everything else. So, for example, think of our solar system and think of the planets in our solar system orbiting the sun. If you could magically replace the sun with a black hole, a lot of people would imagine that we would all get sucked in. But it's not true. Black holes are not cosmic vacuum cleaners. They just have gravity like everything else. And so if you could replace the sun with a black hole, all of the planets in our solar system would happily just go on around orbiting the black hole. Of course, it wouldn't be very nice for us, right? It would get very dark and very cold because there's no more sunlight, but it wouldn't be instant doom. So black holes, as well as being one of the weirdest and most interesting things in the universe, they're also a lot safer than you might think. Okay, that seems like a good place to finish. So I think what I want to do now is go over and answer some of your questions, because I can see some of your questions have been coming in and they are absolutely fantastic. So let's have a look. Okay, so William and Samuel B have asked, what do you think is on the other side of a black hole? It's a very good question. This is one of the most popular questions when people think about black holes. I think the answer is, as I just explained, I don't think there really is an other side of a black hole. I think black holes are quite badly named, right? Because when you hear of a hole, you think of like a hole in a fence that you could climb through and see what's on the other side. A black hole is really the singularity, right? That tiny, tiny speck in space that weighs as much as a star. And so I think there probably isn't another side. If you were unfortunate enough to try and explore the other side of a black hole, it's probably a very good way to get squashed into nothingness. So unfortunately, William and Samuel, I think the answer is nothing. George M, aged 5, says, why can't we see black holes with the naked eye? So black holes, we can't see them with the naked eye because they swallow up all of the light, because their gravity is so strong. So we can see black holes, but we're not actually seeing the black hole itself. What we're seeing is all of the material that's getting sucked into the black hole and kind of swirling around the plug hole. So even though we can't see the black holes themselves, we can see the stuff that is swirling around and falling in. I'm just going to take a couple of seconds to allow some of your questions through. William and Samuel B also ask, where in space do you find black holes? So there, of the two different kinds, the stellar black holes are absolutely everywhere. There are millions of them per galaxy. Every time a big star dies, has to be a really big star, remember, you get a black hole left behind. So where in space do we see black holes? We see them everywhere. But the supermassive black holes are the ones that are really special, and they are the ones that you only get one per galaxy. Chloe, age 10, says, what is the nearest black hole to Earth? It has a long, boring name that looks like a telephone number, unfortunately, because astronomers find so many things in space. We don't get to give them cool names anymore, really. We tend to just give them names that look a bit like a telephone number that tells you where they are on the sky. But I can say that happily for our safety here on Earth, the nearest black hole is about 3,000 light years away, and it's a stellar black hole, so it weighs about as much as 5 or 10 times the weight of the Sun, and it's about 3,000 light years away. Interestingly, it's what we call a binary. So a binary means two stars orbiting around each other. The nearest black hole to Earth is in a binary system, so the black hole is orbiting a normal star. And almost all of the stellar black holes that we've found, so not the supermassive ones, remember, but the ones that come from stars we've found are in binaries, because it's really, really, really hard to find individual black holes, because if they're not gobbling stuff up, and they don't have that whirlpool of stuff getting sucked in that we can see, then it's almost impossible to see them. So the easiest way to find black holes is to look for ones that are orbiting stars. And the nearest black hole to Earth is one that is orbiting a star about 3,000 light years away. An anonymous question asker asks, will the whole universe get sucked into a black hole one day? It's a good question. I can for the universe, the very good answer is the answer no. The universe is not going to get sucked into a black hole one day. The reason is that the universe is expanding, right? So the universe started with a big bang billions and billions of years ago, and it's been getting bigger and bigger and bigger ever since. And there's something with its foot on the acceleration pedal, on the gas pedal of the universe, and this expansion is actually getting faster. It's getting faster and faster and faster and faster, and so it's getting it's far too fast right now for anything's gravity to kind of suck it back together. That effect is called dark energy. This thing that's pushing the universe apart faster and faster and faster. So dark energy beats black holes, and the universe will just get bigger and bigger and bigger forever, and happily for us, will not get sucked into a black hole. I think I answered that one. Sebastian asked, if a white dwarf are the fifth state of matter and neutron stars are the sixth state of matter, do you think black holes could be the seventh state of matter? It's an interesting question. So states of matter are things like solids and liquids and gas, and some people say that white dwarfs and neutron stars, because they are very, very strange objects, you can think of them as states of matter. I don't think it makes much sense to think of black holes as the seventh state of matter, because when you think of matter, you think of atoms, you think of stuff, and it's different ways of arranging the stuff, different ways of arranging the atoms. I think it's very likely that black holes are these singularities, so I think they're not matter at all. I think instead of being a state of matter, I think it's best to imagine that black holes are something like tears in the fabric of space and time themselves. So I think black holes are a lot more strange than anything just a state of matter. An anonymous person says, what is a white hole? It's a great question. So a white hole is a theoretical object that is the opposite of a black hole. So a black hole is something with gravity that sucks everything in, and there's no power in the universe that can let you escape it. A white hole would be the opposite. So it would be a singularity, a dot in the universe that has some kind of anti-gravity, and no power in the universe would let you even get close to it. And so a white hole would appear like a big kind of a big fountain of stuff in space, right, kind of spewing out material, and there would be no way to get near it because its anti-gravity would be too strong. Again, a white hole is something that's theoretically possible. Again, if you take Einstein's equations, you can write down the equation for something that behaves like a white hole. Whether they exist or not is another matter, and I think it's probably most likely, that white holes don't really exist. So a white hole is like the opposite of a black hole, but they probably don't exist, which is a shame because they would be quite cool. Where's the top one now? And the question just vanished. Where are we? Finley says, is the speed of light different in a black hole? That's a really, really fantastic question, Finley. The answer, interestingly, is no. So the speed of light is something called a constant, which means it's absolutely the same everywhere in the universe all the time. So if I measure the speed of light here on Earth, and I measure the speed of light in space, and I measure the speed of light when I'm a rocket zipping through the universe, I'm always going to get exactly the same answer. The speed of light is the same for everyone in the universe, and the same is true inside black holes. So as weird as black holes are, they can't change the speed of light. So the speed of light is exactly the same everywhere, including inside black holes. Excellent question, Finley. Bailey says, how small are black holes when they form? It's an interesting question to talk about the size of black holes, right? Because the actual black hole itself, the singularity in the middle, is really infinitely small. So in the real way, every black hole has the same size, which is infinitely small. But the event horizon is what some people talk about when they talk about the size of black holes. And the event horizon is bigger or smaller depending on the mass of the black hole. Some of the biggest black holes of all, so like those black holes I was talking about before, those supermassive ones that can weigh thousands of millions of times as much as the sun, their event horizon can be bigger than the whole solar system, which is absolutely amazing. So black holes, the size of black holes, it's either infinitely small or it depends on how big they are. That's the question. And as through their life, as black holes get more and more massive, as they gobble stuff up, their event horizon grows. So how small they are really just depends on how much they weigh. How big are black holes if you can even measure them? I think that's the same, Finley. That's really the same answer as the one before, right? So it depends if you're talking about the singularity, and then the answer is infinitely small, or if you're talking about the event horizon, and then it just depends on how big the black hole is. It might be a few miles for a small one. It could be billions and billions of miles for a very, very big one. Georgie, they're swapping around. An anonymous person, Lorenzo, age 7, says, "What is inside a black hole?" So what's inside a black hole again? So what's inside the event horizon is the answer is really just more space, right? What's inside the singularity itself? I think there probably is no inside, because remember, a singularity is an infinitely small dot, just the tiniest, tiniest, tiniest dot that you can even imagine, and it's a dot that's so small there is no inside. So the answer is, yeah, there is no such thing as the inside of an actual black hole of a singularity. Sid says, how many black holes are there in the entire universe? That's a really, really difficult one to know. So first of all, we're never going to be able to count them all. So the best we can ever do is give you a guess. In terms of supermassive black holes, there's one per galaxy. Galaxies in the universe, there's maybe 100,000 million galaxies in the universe. So that would give you 100,000 million supermassive black holes. Stellar black holes that form when really, really big stars die, and there's going to be even more of those. There's millions of those per galaxy. The answer is trillions and trillions of trillions in total. A very, very, very big number indeed. Okay, we're running out of time, so I'll do the last few questions. Georgie is asking a non-black hole related question. Why are the gas giants so much bigger than the rocky planets? It's a really good question. So if you think about our solar system, we have Mercury, Venus, Earth, and Mars, that are these little rocky planets. And then you have Jupiter, Saturn, Uranus, and Neptune, which are the big gas giant planets. So why are the gas giant planets so much bigger than the rocky planets? And the answer is to do with where they form. See, I'm sure you would have noticed, if you look at our solar system, that all of the planets that are close to the sun are little and rocky, and all of the planets that are far away from the sun are these big gas giants. And the reason is that when you're forming far away from the sun, it's you're colder, right, because you're far away from the star. So imagine way back to the start of the solar system, where the sun is just forming and there are no planets left. There are no planets yet. And there's a big cloud of gas, and the gas is all kind of sticking together and making grains of sand and pebbles, and the planets are forming themselves. When you're a long way away from the sun, it's very, very cold, and so it's cold. It can be cold enough for ice to form, and if there's ice to form, you can grow your planet really, really quickly, because the gravity of your baby planet can kind of grab up all the ice. You can think of it like a giant kind of solar system version of Hungry Hungry Hippos, right? There's all the stuff that's around in the solar system, and all the planets are growing as big as they can, and their gravity is kind of gobbling up all the stuff around them, and they're trying to grow really, really big. If you're very far away from the sun, there's lots of ice around, and so there's loads of stuff to gobble up, and so you can easily win the game of Hungry Hungry Hippos and grow really big. But if you're too close to the sun, it's too hot, there's no ice around, and there's just not enough stuff to kind of gobble up to grow big. And so that's why planets that are far away from the sun can grow really, really big, even though planets that are close to the sun end up really, really small. Hector says, why will you die when you go through a black hole? The answer is because you get squashed into the singularity. So the singularity is a thing that is infinitely small, and when you actually go into the black hole itself, like the singularity, the very core of the black hole, you get squashed down into an infinitely small space, which I think would be a very, very unpleasant experience. So luckily, it's probably quite good for us that the nearest black hole is thousands and thousands of light years away. Amara says, is it true that no light gets out of a black hole? It is indeed true. So that's what the event horizon is, right? So the event horizon is the point of no return, that nothing can escape, and light is one of those things. So that is why black holes are black. Where are we? Nor, I think I might make this the last question, because we've been going nearly 50 minutes now. My goodness. Noriel says, why do black holes look like they are glowing around the outsides? That's a really good question, Noriel. So it's a bit counterintuitive, right? You think of black holes as being black. They're supposed to gobble everything up. Why does it look like they're glowing around the outside? So you're not actually seeing a black hole. what you're seeing is all of the stuff that's being gobbled up by the black hole. You're seeing the whirlpool of stuff. So if you think of the black hole as like your plug hole, the stuff that's glowing around the outside is like the whirlpool that's forming